Okay, this slide we talk about the magnetic circuit. So, how to use electricity in terms of power. Mainly, we use electricity, right? In terms of power electric. I have talked that the electricity we can use in signal, right? For electronic device, right? For calculation and to send the signal, to transform it to the wave, right? Communication, for communication, right? To transform it to from voice to electricity signal, for example. So many uh, use of electricity, but in terms of power, mainly we use in heat, right? Just transform this into heat is I square R, for example. And we can use this in mechanical power, right? It's we transform electricity power into mechanical power, right? This theory, we first, before transform electricity to mechanical, is we need to use magnetic coupling, right? We induce movement by magnetic, okay? Induced by magnetic. How the motor work is induced by electromagnetic, right? We uh, produce the rotating field of magnetic field first, right? To move, right? To move the rotor, right? So we talk about magnetic circuit, electromechanical energy conversion, right? Then we go to transformer and motor and generator, right? Which is we can call rotating machine, right? In electric power engineering, we call about machine. The machine it means that transformer, motor, and generator we call it machine. Okay, machinery, electric machinery, right? So in this slide, the content is magnetic circuit and electrical mechanical energy conversion, right? And I will talk about the power transformer. Okay, just give you some idea. Maybe transformer we don't. I will not go to the calculation part, the loss in transformer part. Okay, just you just know how transformer work. It's okay for you. It's just okay for you. Okay. So we people know about electric and magnetic for a long time, right? As we know about Ampere laws and Faraday laws that you have learned in. If you remember, maybe you remember that laws, right? What is Ampere law? What is Faraday? Like that. Okay. So we know that to generate how to generate magnetic field from electricity. Okay, during that time, right? About uh, 180, one 1,800, right? At that year. Okay, and the quantity used to quantify the strength of magnetic field is magnetic flux, right? This is magnetic flux. Is unit of Weber, okay? And the magnetic flux density is Weber per square meter. Or we use this unit in terms of Tesla, right? Tesla is Weber per square meter, right? And then we have one quantity known as magnetic field intensity or H. So we have the relation between B and H, and this is a very the relation between B and H is one of key factor in terms of to use the power of electricity to transform into mechanical power. Okay, mechanical power. Okay, and H is the unit in terms of ampere per meter, right? Ampere. as a vector here, right? Okay. Thus, the density of magnetic flux and its intensity are generally described in vector form in terms of the component present each spatial direction. Okay. And the force that take to the charge, right? To the charge, charge of Q moving. The velocity, the charge force is QV by B, right? When we move the charge, right, in this direction, U is the velocity, right? Sometimes we use V as velocity, right? Velocity of moving, right? But in this case, to avoid confusing with voltage, right? We use U instead, right? QUB. I think you may be able QV cross B in physics, right? Okay, you remember what is formula, right? So this is the force. So if you put the conductor with the current, the move of current is mean the current flow is mean the electron moving, right? The electron move, not electron, the charge moving, right? The charge moving in the magnetic field. So the force will take place to this conductor, right? So if the current flow in the magnetic field, right, there is the force applied to that conductor, right? That wire to that wire. So with this theory, we transform electric power to mechanical power, right? We transform electric power to mechanical power, right? Okay, to mechanical power. So we can generate electricity from mechanical power. We can generate mechanical power from electricity, right? Okay. And we can calculate magnetic flux, right? If we know the B, B is Weber per square meter flux density, right? If we know Weber per square meter, and then we can calculate the total flux from integrate the area, right? Okay, we know the density and we know the area. So total flux is Weber, and this is Weber per square meter, and this is square meter, right? Then we can calculate total flux if we know the density of the flux and area, cross-sectional area. Okay, this just remind you general view of physics, right? Magnetic physics. Okay, and from Faraday laws, right, that we can calculate electromotive force, right, from d phi by dt. E is d phi by dt. This is the kind of electromotive force is the, like a voltage, right? It's the voltage to drive, right? Here. So if the flux change, right? We have flux change. There is the force to drive. Is the voltage will take place. So we can generate electricity if we move the coil in the magnetic, right? If we move the coil close to magnetic field, right? In magnetic field, we can generate electricity. So we can change mechanical power to electrical power, right? Okay, we move, right? We use mechanical power, or we rotate the coil, right? In magnetic field, right? We get electricity, right? So with this theory, we can generate electricity, right? Using mechanical power, using turbine, using hydro turbine, right? Using any engine, right, to drive, and then we get electricity. Okay, this is generator. Okay. On the other hand, we use electricity to drive something, right? This is motor, right? In motor form, like that. Okay. Yeah. Okay. Yeah, and you can use the uh, right hand rule, right, when you would like to calculate, right? But in uh, electrical engineering, we very interested in this uh, equation, right? E is defined by dt, right? And if we have a lot of turn of coil, is n turn of coil, E is n defined by dt. Yeah. Right. So we increase the voltage, right? The electromotive force, right? We increase the electromotive force by put increase the number of turn, right? Number of turn here. N turn coil. Yeah. Okay. Okay. And the flux linkage is calculated by total flux is number of turn into one flux because it's passed to many coil, right? N turn is so it's multiplied by n, right? And the electromotive force may calculate by d lambda by dt. Lambda is total flux, right? Total flux link, right? Total flux linkage here. Okay, it's similar equation, right? Okay, and we have what we have here. Current is the change of charge during the time, right? The charge flow, right? Current is dq by dt, right? And lambda is L into I here. Total flux links here. So V is L di by dt. This is the equation of inductance, right? If we have coil, is the equation of inductance, like V and I. V is L di by dt, right? Inductance here. Okay. Okay, we can calculate also one index called co-energy is integrate between V and I, E and I here. Okay. And for Ampere laws, right? Ampere law state that B equal to B mu H, right? Here is the B is Weber per square meter, right? And H is in terms of uh, flux intensity, right? It's ampere turn, right? Ampere, right? Flux magnetic field intensity, right? Here, H magnetic field intensity. Yeah. Okay. This is ampere laws, right? Mu is the constant value. Mu is constant value. We call the permittibility of the material. It is the permittibility of the material, right? And usually we use the value mu r, right? Is the which is the easier to represent the value of permittibility because the mu r is the value that's easy to use also when it's represented in the term of time to mu zero, right? Mu zero is the permittibility of free space, right? Of the free space, yeah. Okay. Free space, the permittibility of free space is this value, right? And we represent mu of the material in terms of mu r into mu zero of this space. For example, the air is the the permittibility of air is equal to free space, so mu r is 1, right? If for the permaloy is very high, right? So it's 100,000 times of free space here, right? So the material used is the permeability of the material is very important, right? Because if we use this material as magnetic part like this, if we just have a coil, it's the mu zero, right, of permeability, and if we use material like this instead of air, right? Instead of air, we can have very high permeability, right? So this value is easier to for the flux uh, to move, right? For the flux path, magnetic flux, okay? Yeah. With the same H, right? With the same H, we can increase the uh, B, right? We can increase B by using the material, right? The high permeability material, okay? The high permeability of material. H is the H is depending on H is depending on current flow in this and the number of turn, right? H and number of turn, current and number of turn. So with high permeability material, we can increase the uh, flux density. We can increase flux density. Okay. So in transformer, we use the high permeability material, okay? And in motor, in generator, okay? That's why we get the coil turn into the high permeability material. Okay. And for ampere law, we integrate HDL is sigma I, right? Here. And finally, and the electromotive force ampere turn is number of turn multiplied with the current here. Okay, this is the source of the energy, right? Turn and ampere, right? We call this is magnetomotive force. Okay, magnetomotive force. And we can calculate the flux density by mu Ni divided by L, right? Here, flux density of tightly wound circular coil here, right? And for toroidal coil, like this donut shape, right? For donut shape, we calculate flux density by mu Ni divided by 2 pi r, right? 2 pi r2 here. 2 pi r is the range of this. Okay. So in magnetic calculation, your our variable are current flow, right? Current, the relation between current and the magnetic flux density, magnetic flux, magnetic free field intensity, ampere per meter, and the electromotive force, magnetomotive force, and total flux link here, right? Will be our general variable in our calculation. Okay. Okay, this is we call the magnetic circuit. Okay, magnetic circuit. Okay. This is the magnetic flow in when we try to control the magnetic flux, right? To make the flux cross to the our coil. Okay, we have this the path of magnetic line, right? The range of part of the magnetic path is the L. Total range is L, and the cross-sectional area is A. Okay, the range is L, and we assume that the permeability of the material is very high. Okay, is very high permeability. So it means that in this case, the magnetic flux will not lead to a path. Okay, all magnetic will flow in this material because it's easier to flow. Okay, it's easier for magnetic in this to flow in this shape, right? It will not come this path, but in free space or free air, it will go to this path, right? So we control magnetic field by using high permeability material. Okay, this type of material we call ferromagnetic material. Okay, ferromagnetic material. This, okay, this enclosed part of magnetic field. Okay, this part. So no flow. In fact, in practice, this would be some leakage flux here. In practice, most of the flux will flow to the material. Okay, some small leakage. Okay, this is the loss, right? This is the loss. And if we cupping one another coil in this side, another coil in this side, and we supply power here, we can get the power on another side. Okay, in this case, this is a magnetic coupling. Okay, this is a kind of transformer. Okay, this transformer. Okay, in magnetic circuit, we calculate. Okay, Weber is Weber per square meter is Weber per square meter, right? Area, right? And H is B by H, or B equal to mu H, right? Or flux per area, right? B, H is B divided by mu, right? What is mu is mu R mu 0, right? Okay. And the magnetomotive force is N into I, or HL. H into L is the range of magnetic path. L is the range of magnetic path. And magnetomotive force is flux into L divided by mu A. Because H is flux divided by mu A, right? H, yeah. Right? So we just substitute flux divided by mu A, right? And this is L, not 1, this is L. This is the range of path, right? Yeah. So force, magnetomotive force is the flux into L divided by mu A is similar to the equation of V equal to I into R. This is magnetomotive force. The force to drive magnetic, okay? The force to drive magnetic. MMF, magnetomotive force. We have electromotive force, right? Is the force to drive electromotive force, the force to drive charge, right? Electric charge, right? To drive the current, right? To drive the current, and this is the resistance, right? And this is the flux. The flux flow like a current flow, right? It should be something to drive the flux to flow, right? This is magnetomotive force. We call magnetomotive force. So if we form magnetic circuit like this, the force to drive flux is magnetomotive force, right? In this case, we have voltage to drive the current with the resistance of R, right? And this is the resistance. Is resistance of the flux path, right? Is L by mu A. And what is the resistance in electricity form? Is L by sigma A, right? Okay, although L divided by A, right? Similar, right? Similar. But in this case, in magnetic term, right? So we calculate this the magnetic circuit similar to electric circuit. Okay, we can calculate. So we need to compute the magnetic resistance, right? This is a magnetic resistance here. This is magnetic resistance, or we can call it reluctance, right? This is reluctance. Okay. So finally, if we want to calculate magnetic flux circuit, it will be in the term of the reluctance, right? Reluctance. And reluctance is, what is reluctance? L divided by mu A, right? A is the cross-sectional area. L is the path, right? Total range, right? Average range of the flux path. Yeah. Okay. Similar to electric circuit, just similar to electric circuit. Okay. Okay. So this is the relation between electric and magnetic circuit, right? Electric quantity, we have electric field intensity E, but in magnetic quantity is magnetic field intensity H, right? The voltage is E. And in magnetic term is electromotive force, right? Or F here in ampere turn. I into N. Current I, the magnetic flux in Weber. Current density J is magnetic flux density in B, right? Resistance R, this is reluctance, right? Reluctance. And this is conductivity. And this is permeability, right? Similar value. This is similar value, right? Okay. So the force to drive the flux in magnetic field circuit is come from current, right? Current and number of turn, right? We generate flux by this. We can generate flux by this method. Okay. Okay, here. Right. So if we have different reluctance in magnetic part, right here, we can just combine, similar to we combine resistance in the circuit, right? So for example, this magnetic field circuit, right? We can use this symbol, right? Analog circuit representation. We have magnetomotive force here, which is ampere turn, right? This is ampere turn, right? This ampere turn, and we drive the flux here. So this part have L2 and this have L1, right? If we calculate, this is uh, L divided by mu A of this part, L divided by mu A of this part, right? Different parts and we connect together, right? We have two R1, right? This R1, two R1 and two R2, okay. Yeah. So in series form, we just uh, add it together, right? Add together in this circuit here. Okay, like this. I think we see this example and it's enough for today, right? Okay, let's see this example. Sorry. Sorry. Okay, we have the magnetic circuit, right? We given data is mu R is 1000, number of turn is 500 turn, and the current is 0.1 amp. The cross section area is this. Okay. Oh, where is the figure? Oh, this is figure, right, of this example. Okay. Here. Okay. And this is the area, right? Area. Y.1, right? Here. 0.01 meter. Okay. So the cross section area is 0.01 square, right? Square meter, right here. And we know the range. H is 0.1 meter and L is 0.1 meter here. We just calculate, right? We just calculate the cross section area, right? And magnetic path range, right? So in this case, the force is how many turn? 500 turn, right? 500. We have 500 turn, right? The force would be I into M is 0.1 into 500, right? So it's 50 here, right? Yeah, ampere turn, 50 ampere turn, right? That's correct. Ampere turn. Yeah. Then we calculate the mean path. Okay, the average range of magnetic path, right? So we calculate this range, right? The middle range, right? In this case, they call mean path, right? The middle range, right? So this is 0.09 meter, and then 0.09 meter each, right? So the mean path is 0.09 multiplied by 4 is 0.36 meter, right? This is L. Okay. The cross section area is same for all, right? So we can calculate the reluctance by L divided by mu A. So L divided by mu is mu R and mu 0, right? Mu R we know here 0.36 divided by 1000 multiplied with 4 pi 10 power minus 7, and this is cross sectional area, right? Mu 0, where is mu 0? Mu 0 is mu of free space, right? This is mu of free space is this value, right? We use this value. Mu 0 is mu free space. Yeah. So we have the reluctance of 2.865 multiplied with 10 power 6 here. Okay. Okay. Now we know magnetomotive force and the reluctance, right? What we know is magnetomotive force is ampere turn, right? And L by mu A, right? We know this value and this value, right? Then we can calculate the flux of magnetic, right? The magnetic flux. Okay. Then we calculate magnetic flux by magnetomotive force divided by reluctance. So we get this flux, number of flux in Weber. And from number of flux, if we divided the number of flux by area, we will get flux density, right? The flux density, right, of this area. So this is the flux flow, right? Flux divided by the area, right? We get flux density, right? In Weber per square meter. We get flux density here. Okay, and we can also calculate magnetic field intensity is B divided by mu, because B is mu H, right? Then we get B divided by mu is 139 ampere turn per meter. Okay, I think I will stop this. Then you can check your understanding by try to do this, right? Can you do this? If this is the magnetomotive force, right? This should be, this is reluctant, this is reluctant, this is reluctant, this is reluctant, this is. So you calculate reluctance of each part, right? Then you will get this circuit, right? This circuit, right? Reluctance of each part, right? The reluctance of each part is L by mu A of each part, right? Okay. Finally, you get this circuit, right? And can you calculate flux, right? So you need to get resultant of reluctance, right? Then you can calculate the flux. This is Req here. This is the answer, right? You can check your understanding, right? If you try to do this slide, I think it will make you get more understand, right? So you will get clear of your understanding. Okay. Okay. Any question? Okay. Just try to do this slide. I think it will remind you. If you do it today, it's very good for this slide. Okay. Okay. This is next time I will get into air gap. If we have air gap, what happened? We have a very high reluctance in the circuit, right? What happened if you make a force here? Okay. Okay. We are not going to this homework yet. This we leave it for next time. Okay. Too much or not? It's in fact it's